In this segment, we're going to close the loop on some of what we've been looking at and come back to the idea of doing this semantic parsing, converting to lambda calculus expressions using Seq2seq models now. So we're going to view this semantic parsing as a translation problem where we take an input like what states border Texas, and we map that into this lambda representation. I've written it out in this tokenized fashion here, where basically each thing separated by white space is one unit that we are going to generate from our Seq2seq model. So the steps here are that we have to write down a linearized form of these semantic parses, train a Seq2seq model on it, and then it will directly predict into this representation without any need for intermediate structures or grammars like CCG. So the benefits of this are that it makes this process of grammar engineering and coming up with these latent derivations and this latent variable training much, much easier, and that we don't have to deal with any of that stuff. However, there's some issues here. One is that this thing might produce invalid logical forms. So for example, how do we know that it actually produces the right number of closed parentheses at the end? The Seq2seq model is just kind of going along and spitting out tokens until it decides to emit stop, and it's learned end-to-end with backpropagation. There's no constraint that it has to produce basically the right number of closed parens unless the training has told it to do that. And then the second question is, does this actually work? So one thing that was useful in order to make this work, which was explored by Robin Jia and Percy Liang, was they looked at how to encode the same kind of invariances that we might be able to get at in grammar-based models in Seq2seq models. So when we have a parser, what states border Ohio and what states border Texas, it's pretty easy to get the parser to handle these in similar ways. Depending on what features you have, you might have very small differences in how this gets handled, but it's not going to be dramatically different. But we have no guarantee that the Seq2seq model is going to want to treat these cases symmetrically, right? It might be that in its training data, it only saw Texas, and so when you see Ohio at test time, it's just going to have no idea what to do with that token and just explode. So they looked at when they were building a Seq2seq semantic parser in this framework, and they were some of the first to really explore this. They wanted to know if the Seq2seq semantic parser could handle these things in the same way. And their idea was to use a technique called data augmentation. Data augmentation is very common in computer vision, where what people will do is if you have a picture of an object and you're doing some kind of object recognition, you can translate or crop that image and produce various transformations of that input data that should still have the same label. And so then the model should be able to handle translated and cropped images. So we can do the same thing here and automatically generate some training examples that are going to allow us to teach our model that, okay, whatever token occurs in the state slot here, put that into the output. And so what they did was they had a way of abstracting out things like states. So they came up with a rule here, and again, this kind of looks like actually using notions of grammar, but really it's much simpler than the CCG grammar before, and that they're just kind of mixing and matching some pieces. So they abstract away the state and come up with the string what states border state ID. So this can match any question that looks like that. And then we have the corresponding lambda calculus expression where we've again abstracted away state ID. And so now we can plug in basically any state and its corresponding name and produce a training example that is correct, that encodes this invariance that, okay, whatever state you put in the natural language should just show up in the logical form as well. So it lets us synthesize a new example. If we just see what states border Texas during training time, now we can get what states border Ohio. And it lets us do this kind of remixing of our data. And so they explored this and some more complicated versions of it as well. And they were able to apply their framework pretty broadly. So they looked at three different data sets or settings with three different representations. So GeoQuery, which is a data set about these kind of place questions, is represented in Prolog. ADIS is in a lambda calculus representation, and the overnight data set, which they produced in some prior work, is in kind of other domain-specific languages here. So I've been a little bit imprecise talking about these different logical forms, and I've tended to use lambda calculus here. The differences between these things aren't that important to get into from the standpoint of this course. And fortunately, Seq2seq models make it easy to map into any of them. So this is very nice because otherwise it's very difficult to handle all of these things. You have to do a lot of engineering, and they could just do it all uniformly. And so compared to prior work, you might be thinking, oh, neural nets, of course, it's going to crush everything that came before. And that's actually not what we see here. So when we look at their model with no data recombination here, the kind of just basic version, they're actually doing pretty substantially worse than some stuff that was much older. So for example, this system by Parsing et al. In 2011 was getting 91.1, and now they're down to 85, right? So this is like almost double the error rate. So, but it turned out that with all of this augmentation stuff, which is basically all these are different kind of augmentation schemes, they were able to get up to performance which was nearly as good as the systems that were there before. So these forms of augmentation all make things better, and then again, it's not as good as the hand-tuned systems that we had 10 years ago, but the ability to do all these things uniformly and just to make it much easier is really, really powerful. So then going forward, people can sort of explore these for other problems like predicting regular expressions that are described in natural language. Like lines ending in Q, you kind of output this regex that looks like this, right? And again, you would have had to engineer a whole separate grammar and everything to deal with this in the semantic parsing framework. You do need a lot of data, so that's kind of one downside of these approaches. But it also doesn't necessarily scale that well. So they're really handling very simple descriptions in this work. So there are definitely shortcomings of the Seq2seq approach, but it's nice that you can kind of just throw it at a problem, collect some data, and see what sticks. And then the last thing I'll talk about here is generating SQL queries. So this is actually one of the biggest applications of this stuff that people are working on nowadays, where you have a question and a database, and you want to actually turn that question into a SQL query that you can execute against that particular database. So the big difference here is now, rather than assuming like, oh, okay, we're handling our geoquery questions about states bordering stuff, we know all the semantics. Now it's like, I could theoretically hand you a new database and a new set of queries and say, all right, give me some, a new set of natural language questions, and say, give me a new set of queries. So the challenge here is that we need to kind of deal with all the syntax from SQL and produce this expression. And so in this work, what they did was they actually used 3 different Seq2seq models to generate the different parts of a select statement in SQL. And the thing that we haven't talked about, which is going to be really important for this, is how do we deal with these column names like engine? In general, they could be drawn from just a very large vocabulary, and we may not want to deal with that because we know that for a particular database, there's only going to be a few column names. And so really this should be formulated as a task of like picking from between the existing column names. And so this is going to set up the idea of pointer networks or pointer mechanisms, which we'll talk about in a later segment. And another question is, how can we improve all of this stuff by kind of tracking the input more closely? And I'm going to talk about what that means exactly later when we get to the idea of attention. But for now, we've seen that we can apply Seq2seq models for all these different kind of language into some sort of formal representation or code type problems. And while it's not perfect, it still works pretty well and is very, very flexible. That's the end of this segment.